I'm going to give a fairly brief talk now, just picking up on a couple of other things, and then we have two more talks to follow that from Cardo and John, and then we'll have a general discussion at the end. So I'm going to focus on two aspects, estimands and feedback loops. But I did just want to point out first of all that there is a part answer that will get us some of the way there. We're not totally in the dark and reinventing the wheel when it comes to counterfactual prediction. So an approach that's quite often used in practice at the moment, and we can debate how useful it is to estimate causal effect of an intervention from a randomized controlled trial, develop a predictive model from our observational data, and then apply the relative treatment effects from the randomized controlled trial to the estimated outcome risk from the observational data. So this is a relatively simple solution, which makes quite a few strong assumptions, but at least gets us some of the way there. And this is done in practice. For example, the predict breast cancer risk model does something along these lines. And Q risk, when it's illustrating the benefits of taking a statin, follows this kind of approach. So I just wanted to give some balance and present a simple solution that at least gets some of the way there. Okay, so the first thing I wanted to mention is estimands. So and that's the question of what does our prediction mean? So the important point, as Carla talked about in detail, is that the expectation of the outcome conditional on the treatment is not the same as the expectation of the outcome in a future patient, given that we intervene to set it to give them a particular treatment. And more than that, we can also think about this as a problem happening over time. We typically make predictions that look into the future. What's your risk of heart attack in the next 10 years? And in that, we then also have the problem of treatment drop-in. And in that vein, we can ask three different related questions. So what's the expectation of the outcome given we don't treat now, today, when we're making the prediction? What's the expectation given we don't treat now or ever? Or what's the expectation given we don't treat never, now or in the next 10 years, say? So now we're sort of asking a question that's got something to do with the future, whereas, of course, we can only make a prediction based on what we know up to the time where we are. So I should also, I just want to briefly say as well that Romin very nicely in the paper that I'm highlighting below distinguishes between guided treatments and background treatments. So in other words, the guided treatments are those that we are using our prediction model to determine whether to give or not, whereas background treatments are those that we're, are sort of happening in the population that we're not interested in for this particular decision. And they, and they need to be handled differently. So treatment drop-in is a problem of, and the key problem here is essentially treatment confounder feedback, where decisions of people in the past of whether they get treatment in the future depends on the progression of their risk factors. So whether their blood pressure starts going up and up, they're the ones that get treated. So just simply censoring people or excluding ones that start getting treated later will not give us the right answer. We'll have bias because of that issue. But of course, this is a problem that's been considered for a long time in causal inference, and we have methods like marginal structural models and related techniques that can be used to solve this problem. So treatment drop-in, as I say, something that we need to think about very carefully when predicting into the future. And it does matter. So we looked at predicting cardiovascular disease risk in a population in the UK with a 10% treatment threshold, which is used in practice prescribing statins. And by looking at treatment drop-in, that moves about 3.5% of the population from not being treated to being treated. And the other thing that I wanted to mention is the fact that as soon as you make a prediction, or as soon as you deploy a prediction model, it changes the way that that people behave. And the picture on this slide is Harry Seldon, who's a fictional character from Isaac Asimov's Foundation series. And he founded a field called psychohistory, which is all about predicting the future. But he had an important caveat for this, which was that you can essentially predict the future, provided that the population should remain in ignorance of the results of that prediction. Because as soon as somebody's aware of what the future holds, the behaviour changes, and therefore the prediction will no longer hold. And you can see that for prediction, this causes a problem, because as soon as we deploy a prediction model, that changes everybody's behaviour, and therefore the predictions in some sense are wrong, because the people who've been observed to be at high risk have changed their behaviour or received interventions in order to control that. And thanks to Romin and Rolf, who I know is here as well for this slide. I hope I do justice to the explanation. So here we imagine a scenario where we try and account for the fact that you know, so for the first 2,000 patients here, nothing's happening. So we imagine here that that there's no treatment available for this particular condition, and we're basing our model on the first 2,000 patients. But now we keep updating our model, and at patient 2,000, a new treatment is introduced, and we either decide to offer this treatment to patients who are at high risk according to this model, or not. And if we offer it to people that are at high risk, then they take the treatment and that reduces their risk. So then if we're fitting the model based on the data of those patients who were at high risk and now have taken the treatment, that changes their risk. So the model is now going to essentially recalibrate itself, and the threshold at which people are at risk is going to change, because the model has now recalibrated itself to account for the lower risk we see, because all the high risk people were taking this intervention. And this is going to end up as shown in this bottom figure, where we assume people being treated. This is going to essentially end up with a cycle where people are treated, therefore not many have the outcome, low risk. So the model starts to predict that everybody's at low risk. Nobody gets treated, everybody has the outcome. Therefore, everyone's at high risk. The model starts to predict high risk, and then everybody gets treated again. So we'd end up potentially with these cycles of high to low risk being predicted, and therefore changing treatment behaviour. So that's you know, sort of caveat on why we'd need to be careful with updating a model and not correctly using the sorts of things we've been talking about today to account for the effect of treatment on the outcomes amongst the people. Okay, I've been deliberately brief with my slide and have sort of cut it down well in the last few minutes, just to try and get us back on time. So I haven't presented all of these things that I'm summarising, but say I've mentioned that there is a simple solution to this problem which gets us part of the way there. But this does come with some challenges. So estimands, as I talked about, so what is this treatment naive prediction? What does that mean? Selection bias, I didn't talk, and validation challenges, I didn't talk about in detail, but Carla talked about both of those in her talk. And of course the prediction paradox and feedback loops. So I'm going to leave it there.